Hey guys, welcome back to Cougar Chem Tutoring. I am Austin, and I'll be running through part 3 of problem set 12, Lewis structures. Pardon my voice, I am a bit sick right now, but I did want to get this in before this was due, so I'm doing this as soon as I can. Okay, number 8. Draw the Lewis dot structures of the following, including all resonance structures. Indicate any non-zero formal charges and any atoms that do not follow the octet rule, and give the bond order for each type of bond. Okay, first we're going to determine the center atom. So of all the ones that can make bonds, boron's in the third group of the periodic table. So it's got 3 valence electrons, which means it potentially could make 3 different bonds. Okay, where fluorine's only got that one area where it can do it, right? So assuming that boron can make the most bonds without expanding octet, I'm going to assume that it's the center atom. So I'm going to put boron in the middle and then draw my skeleton. Okay, here's my fluorine, here's a fluorine, and here's a fluorine, and give everybody an octet. Okay, now I'm going to count the valence electrons. So I've got 3 here and then 3 times 7 here. So that's going to be a total of 24 valence electrons. And if I look here, I've got 8, 16, 24, 26. So I actually have too many electrons here. Now, if you remember from the last video, when we had an example like this one, it was gallium. Boron is one of those few electrons, or elements, excuse me, that will actually be happy with less than 8 electrons, 8 valence electrons, and I'll show you why. Remember, when we're doing formal charges, we're always doing what they want minus what they have. Want comes from where they are on the periodic table, and have comes from the Lewis structure. So on the periodic table, because boron is in the third group on the periodic table, it usually wants 3 electrons assigned to it, not valence electrons assigned to it, and I'll show you the difference here in a second. And what it has is going to differ from what it is on the periodic table. Now I'm showing you this because we're going to have to erase this lone pair from boron, but it ends up being okay because if you look at each fluorine, remember each fluorine wants 7, and it has 2, 4, 6, and then half a bond, which is 7. So each of them has a 0 formal charge. So I'll put 0, 0, 0. And then boron, because it wants 3, it actually has a half a bond to each of these, right? 1, 2, 3, 3. So it's happy not having an octet because it has a 0 formal charge. And this is one of the few elements that does that. In fact, you'll only see usually boron or gallium that will accept less than an octet, but that's only because they love having a 0 formal charge. Okay, so now they want us to indicate all non-zero formal charges, which I've written the ones that are 0. But in the future, for the next ones, I'm just going to write the ones that are non-zero. And then any atoms that do not follow the octet rule. Well, boron does not follow the octet rule. So boron, I'll just put does not equal octet rule or something like that, okay? Hopefully you get the idea that it's just not following the octet rule. And then give the bond order for each type of bond. Well, you can kind of tell there's not really resonance here, so there's no... we're not going to have to worry about like half of like 1.5 or 2.5 or 1 1/3 bond order or anything like that. We can just say the bond order for a B to F is just going to be 3, or sorry, 1. There's 3 of them, but 1. So the bond order, I'll just say of B to F is equal to 1. Okay. All right, so letter B now. We got the nitride ion. So hopefully you have this one memorized already. Nitride looks like this, okay? Now, if I could write the Lewis dot elements for each of these, but let's just assume that nitrogen is the center element because it can make the most bonds. It can make 3, remember? So I've got my skeleton here. Give everybody an octet. And then from there, I'm going to count my valence electrons. I got 5 coming from here, 2 times 6 from here, plus 1. So that's a total of 18 valence electrons, okay? So I've got 8, 16, 18, 20 here on my Lewis structure. So what I have to do is cancel out at least 2 of them. Oops, yeah, 2 of them right there. So I'm going to make a bond out of that, and then see if those match my my valence count. So now I've got 8 here, and 2 here. So yeah, we're good here. This is going to be one of my Lewis structures. So now that we've matched the valence count, we're going back to formal charges. So remember, this is an ion, so I'm going to bracket this guy because we're going to have to end up drawing a Lewis structure. In fact, let me go ahead and give myself some space to draw that Lewis structure. So we have this end in the middle, and then we have, let's say, a single bond to an oxygen here, double bond to an oxygen here. Okay. Now, if we look at the formal charges, remember the formal charges are want minus have, okay? And this oxygen here wants 6, and it has 2, 4, 6, and then half this bond, which is 7. So that means it's going to be a minus 1 charge here. You'll notice that nitrogen is going to be a 0 because it's got 2, 3, 4, 5. And then this last oxygen will have a 0 as well, because it has 2, 4, 5, 6, which it wants 6 as well. So this is going to be one of the Lewis structures. So let me erase this so you can kind of see. This would be your final answer, as one of the Lewis, not the final answer overall, but for this particular resonance structure is what you're going to draw. Now you can easily tell that this double bond could have been on this oxygen. So I'm going to switch that up a little bit. I'm going to say over here, oxygen, and then double bound to nitrogen, and then single bound to this oxygen. And now this formal charge is over here. Okay, so those are all the resonance structures, and they wanted non-zero formal charges, which we've indicated here. And none of them break the octet rule. They all follow the octet rule. So now what we have to decide is the bond order. Now, the important thing is because this has a resonance structure, either one of these is representing, both of these are representing a possible way that the electrons could be. And now, if you remember back when we were talking about delocalization, we were talking about making a hybrid resonance structure. So actually, I'm going to show you how to do that. So what you do is you draw the skeleton like normal. So I'm going to draw a skeleton here, except notice that on both Lewis structures, each oxygen has 2 lone pairs that stay there, so they're constant. So I'm just going to draw nitrogen or oxygen with 2 lone pairs, and then another oxygen with 2 lone pairs, and then this lone pair on nitrogen also stays there. Okay, and then I'm going to bracket this guy and put a negative. And then what happens is, because I'm demonstrating that these electrons that can move here or can move here, right? Because the way that we demonstrate that is by saying, okay, technically then they can be in both of these at the same time. And in fact, they are, and they're in it literally at the same time. So when you look at this, when you look at nitride, if you were to see it under a microscope or something, or if you could actually see it with an electron microscope, you would find that the bond here and the bond here is exactly the same. And the way that we calculate a bond order for something that's resonating between 2 different bonds is we take the number of bonds, 1, 2, 3, and divide it by the number of atoms with which the center atom is making those bonds. So when I do that, I take so the bond order here. In here, technically, if you were to think that this resonance structure was just the way it is, you would think that this is a 1 and this is a 2. But in reality, it's sharing that extra pair of electrons between the 2 bonds. So the bond order here is going to be 3 over 2, because we had 3 bonds, 1, 2, 3, divided by 2 oxygen atoms. So that's a 1.5 bond order. So this here is the bond order. Now think of it like this bond right here is like not quite it's stronger than a single bond, but it's weaker than a double bond. It's right in between. It's got a 1.5 bond order. And so that's kind of how you'll work with bond order, especially when we're dealing with resonance. That's really when like a funky looking bond order, like a 1.5 or a 2.5 are going to be present. Okay. And that's about it for this problem. Okay, so as long as you got those 2 resonance structures and then the bond order correct, you should be good. You did not have to write the hybrid. I just wrote it to show you what it actually looks like. This is real life. Okay, this is the delocalization that we talk about, the delocalization when we're talking about the hybrid resonance structure. Okay, hybrid, just incorporating all the resonance structures together. Technically, I left this a little bit incomplete. This should say lowercase delta negative here to indicate, because on each of these oxygens there was a negative charge at one point, and it's not going to be a full negative charge in actual structure, so we have to say just partial. Okay, so that would be an example of a hybrid resonance structure. All right, now letter C. This is kind of funky. We did this one in the last video where xenon was the center atom. And it can do that because it's past the 3rd period, right? So even though it's a noble gas, it has an octet, but in order to accommodate all the bonds, it will actually expand its octet because it can. Okay, and we don't technically like to do that, but we do that when it's necessary to accommodate the bonds in the compound. So what I'm going to do is draw xenon in the middle, and then my 4 fluorines on the side and my skeleton. Okay, and then I'm going to give everybody their octet. Okay, and then xenon already has its octet technically here, but when we count these valence electrons, I got 8 here and then 4 times 7 here, so that's going to be 36. Okay, now if you look here, there's 1, 2, 3, 4 times 8 is 32, so I'm actually short 4 valence electrons. Okay, so 36 minus 32, that's going to be 4, which means I have to add 2 lone pairs to this structure, and where you'll always add it to the the element that's expanding its octet. In this case, that's xenon. Remember, fluorine can't do that. It can't expand its octet because it's in the second period, and those that are not in the third period or below cannot expand their octets because they don't have du orbitals open to them. So that means I have the two lone pairs here, and if you count them again, you'll find that you get 36. Okay, so this is the Lewis structure, and in this case, we're not spreading out charge, and we can't really resonate anything. So this is the final Lewis structure. There are no resonance structures for this thing. So now, and what we can also indicate is that xenon is not following the octet rule. So I'm going to put xenon does not equal octet rule. Okay, so that's going to be key for this problem. Careful, sorry, I'm getting a little messy here, but that's for the upper problem there. So it's not following the octet rule. Whoops. It's not following the octet rule because it's got 2, 4, 6, 8, 10, 12 now, right? So it's breaking the octet rule in this case. So now we need to indicate formal charges. So remember, fluorine wants 7. I'm going to put W minus have. Okay, it wants 7, and in each of these you'll find that they have 7, right? 2, 4, 6, and then half this bond is 7. So I'm going to say minus 7 is 0. So because they're all 0, I'm actually not going to put 0 there, okay? Oops, that's not what I wanted to erase. But let's look at xenon here. Xenon, okay, what does it want? It's in the 8th group of the periodic table, so I'm going to put 8 here. It has, and what does it actually have? It's got, whoops, not the whole, remember, only half a bond. So 1, 2, 3, 4, and then both lone pairs. 4, that would be, sorry, 4 plus 2 is 6, plus 2 more is 8. So that's a total of 8. And that means it has a 0 formal charge. And because it's 0, I'm actually just going to not put it on there because they only want non-zero formal charges on here. So this is my final Lewis structure. I don't have to adjust anything. And there's no negative charge to have to distribute into a more electronegative atom or anything. So this is the final answer. Okay, as long as you have this, and then I guess we have to do the bond order, huh? So bond order, bond order of Xe to F. It's just going to be single bonds, right? So that's just going to be 1. All right. On to letter D. Okay, so this is this is kind of a funky one. So I'm going to assume that chlorine is the center atom. Why? Because it can expand its octet to accommodate all these bonds. Otherwise, it would only be able to make one bond, and we couldn't make this molecule if that was the case. So I'm going to draw my skeleton, put chlorine in the middle, got fluorines. Give everybody their octet. And both of these are in the 7th period in the periodic table. So technically what I'm going to say is I'm going to put 7 times 5 since there's 5 of them. 1, 2, 3, 4, 5. Okay, and so that's going to be 35. Okay, plus 1 is 36. So there should be 36 valence electrons here. But if you notice that we got 1, 2, 3, 4 times 8 is 32. So I, again, have to add those lone pairs to the center atom because it can accommodate those lone pairs. We can't just like get rid of valence electrons. They're always going to be there. So now what we have to do is determine whether or not this follows the same valence count, which it does now. But now we have to figure out, following the rules, what the formal charges are, okay? So fluorine and chlorine both want 7. So I'm going to put 7 minus half. So for the fluorines, each of them have 7, right? 2, 4, 6, 7, half that bond right there. So this is going to be 7 equals 0. So I'm going to leave all the fluorines the way they are. But let's look at chlorine really quick. It wants 7 as well. But what does it have? It has 1, 2, 3, 4, half of each of those bonds, right? So 4, 6, 8. So it's got 8. 7 minus 8, that's a minus 1. Now, can you see why it would be why it makes sense that this is a minus 1? Because this overall, whoops, include the lone pair there, has a negative 1 charge, right? And it has to be accounted for somehow in the formal charges. So so we have to indicate that on the chlorine. Now, it's not going to share that. It's not going to resonate that because there's nowhere to resonate that. If I were to do that to make a double bond with the fluorine, I would be breaking the octet rule for fluorine, and it cannot expand its octet, so it's not going to do it. So this would literally be the structure that for your Lewis structure. Okay, and there's no breaking. Fluorine is not breaking the octet, but chlorine clearly is, right? It's got 2, 4, 6, 8, 10, 12 valence electrons, as opposed to the 8 that it normally wants. So I'll say let's see, chlorine, no octet rule. okay? And then, and the bond order here, just between chlorine, the bond order between chlorine and fluorine is just going to be 1, right? They're all single bonds, so I'm just going to put 1 right there. All right, last one, ozone. Ozone, if you don't know, is O3. Okay, kind of funky. We got, so you can kind of assume what the center atom is, right? There's nothing really else. So I'm going to put 2 oxygens over here and give everybody an octet. All right, so ozone is really funky. So this is going to be 3 times 6. This is going to be 18 valence electrons. So I got 8, 16, 18, 20. So I've got too many here. So what I have to do is get rid of 2 lone pairs and then make a bond out of it. So do that. Now, we had to do that to not only match the valence count, but make sure that everybody still had their octets. Okay, that's the beauty of doing that rule. So here, what we're actually going to do is when we assign these formal charges, you'll see that they're actually kind of spread out and that we can't do anything about it. So remember, oxygen wants 6. Okay, so it's this oxygen right here has 2, 4, 5, 6, half of each of those bonds right there. So that means this has a 0 formal charge, and I'll just leave it off since they don't want us to indicate that. So I'm going to leave that there. But if we look at this oxygen, remember it wants 6. This guy has 2, 3, 4, 5. So that's a +1. So I'm going to put a plus right there, okay? And because ozone is neutral, I have to assume that there's going to be a negative charge somewhere. Because if there's not, then it's not going to, we're not going to conserve our charge. This should be a neutral molecule. So so when we look at this oxygen right here, it's going to be 6, 2, 4, 6, 7, 6 minus 7. Okay, so it's going to be a -1 charge. So this has the -1 charge, which makes sense because we need this to be a neutral molecule overall. So because the charges are spread out, we actually bracket these because there are charges within this, and then we just put a 0 at the top. Not very common because usually when we're dealing with ions, they're usually actually charged molecules, right, like polyatomic ions. But ozone, it's charged, but at the same time, it's not an ion because there are no it's spread out its charge, but there are no actual overall charge on this molecule. So because it has charge, though, it can resonate. Okay, so when we draw this again, I have to actually draw this guy on the other side, right? So right here. And then you just have to switch the formal charges, right? So this was a 0. I'll keep that out, but there's a positive one here and a negative one here, and this overall had a 0 charge. So kind of funky, right? So the bond order, if you look at it, right, we're resonating between this bond and this bond, and there are 1, 2, 3 overall bonds. So remember, bond order is equal to bonds over atoms, and atoms, I'll say bonded to the central atom. I'll just put center atom, okay? So that's what you want to use for bond order. So bonds, in this case, we've got 3. Okay, and then we've got 2 oxygens. Okay, it's being spread. Those bonds are being spread amongst 2 oxygens. So in this case, this would be a 1.5 bond order. Okay, and we're not breaking the octet rule here for anything, so we're not going to indicate that anything is breaking the octet. So this is the final answer. This should be what you write on your problem set. And I hope this kind of made sense. I know ozone is kind of one of those funky ones, but hopefully going through these together kind of helped you figure out the pattern that we use to draw Lewis structures. Okay. All right, number 9, last one. Last problem, but multiple questions. So arrange the bonds from shortest to longest and state which would have the lowest bond energy and which would have the highest bond energy. Explain the reason in the trends in the bond length and strength. Kind of intuitively, if you think about a single bond, that's going to be it's going to be weaker. It's going to be weaker and longer. So because it's just a mere single bond. Okay, it's only holding these by one bond. But think of it like if in a double bond, if you were to grab somebody with both your hands, that's kind of a stronger bond, and you kind of pull somebody in tighter. When you pull somebody with one hand, you can kind of keep them at a distance because your other arm isn't locked to them or anything, right? You can kind of spread out a little bit, but once your second hand is on them, you're kind of locked in this place, and it's a lot stronger. So I'm going to draw all 3 of these, and we're going to say this way we're increasing. What are we increasing in? We're increasing in strength. Okay. So if you had a third hand by any chance, you could grab somebody really tight, and then it would be even stronger to break those bonds because you have to break, your 3 arms in order to break that bond. So increasing strength, but if we look this way, this is increasing length. Okay, So they're opposites. So as your length increases, your strength decreases. They're inversely related. Because if you have only a single bond, it's kind of more spread out. Once you get a double bond, they kind of shrink in tighter. And once you get a triple bond, they're even smaller. The bond is even shorter. And you can think by default that they're going to be even harder to break because they're smaller as well. And they're just stronger, okay? So here in this part 1, we were dealing with number of bonds. But this also takes place when we're looking at the size of the molecules. So if you were looking at a periodic table, you'd notice that it goes chlorine, bromine, and then iodine on the 7th group of the periodic table. Okay, they're halogens. These are the halogens. If you remember from the periodic trends, which way did size increase? Increased downward, right? So we're still dealing with length, but instead of length of bond, we're still looking at length of bond, but now we're looking at length of bond because of the size of the molecule and not because of the identity of the bond itself. So if I'm going to draw CCl, CBr, and then Ci. Okay, knowing that chlorine is the smallest, right? I'm going to have this increasing. This is going to be increasing length, right? Increasing length this time. Okay. And in this case, we're going to have increasing strength the other way. So in theory, it's going to be easier to break a Ci bond than it would be to break a CCl bond because the distance between C and like carbon and iodine is bigger. And so it's easier to break that bond. Whereas because these are tighter on chlorine and carbon, it's going to be harder to break them apart. Okay. Again, that length and strength are inversely related even when it comes to size of the atoms. Okay. All right, last one. It says NO plus, NO2 minus, and NO3 minus all involve nitrogen-oxygen bonds. Which would have the shortest bond, which would have the longest bond, and which bond would be the most difficult to break and why? Well, the most difficult to break will be the one that's the shortest bond right here. Okay, so they're going to be the same one. So we're just going to assume those are the same. So now we have to draw a Lewis structure. So I've got N and then O, and then I'm going to give their octets. Now, if I look at NO plus, I've got 5 plus 6 minus 1, right? Because we're short 1 electron. So this is a total of 10. And if you look here, I've got 8, 10, 12, 14. I have way too many here. So I'm actually going to erase these guys, make a bond, and then erase these guys and make a bond and recount it. Now I've got 2, 4, 6, 8, 10. Okay, so now I'm good. Now, if we look at formal charges, remember nitrogen wants 5. Let's see, wants 5, so this is going to be for nitrogen. Wants 5, how many does it have? It's got 2, 3, 4, 5. So it's got 5, so this is a 0 formal charge. Now for oxygen, remember, oxygen wants 6. And what does it have? In this case, it's got 2, 3, 4, 5. Okay, so that means it's going to have a +1. Now, you'll notice that oxygen is the more electronegative atom. However, if we were to move the positive charge to nitrogen, we would by default have to break the octet on oxygen, and that is not favorable. It would prefer to have an octet and be positively charged. Okay, so unfortunately, we can't really do much about it, and this would be our final Lewis structure. Now, if you look at the bond order, okay, the bond order here is going to tell us both the strength and the length. So the bond order here is 3, which means this is pretty strong. So I'm going to say strong and short, okay, because it's a triple bond, so you can imagine it's harder to break, and it's really short. So unless these other two molecules are have a higher bond order than 3, which is extremely rare, then I'm going to assume that this has the shortest bond and it's going to be the most difficult to break because of the energy of this bond. Okay. So let's do NO2 minus really quick. NO2 minus. So I've got N in the middle. I've got my two oxygens. I think we did this one earlier, right? So we ended up having to erase. We had this one down here. We ended up having to erase 2 of these and then making a bond out of this. And then we had the 2 Lewis structures, right? So I'm going to put that. Oh, I should have bracketed this guy here and then put a plus here. But this had a bond order of what? Whoops. Bond order. This is 1, 2, 3 divided by 1, 2. So that's a 1.5 bond order. So this is definitely weaker than the bond order of 3, but we don't know if it's going to be stronger or weaker than the one that's in the nitrate that they've asked us to draw as well. So let's draw that one really quick. We got nitrogen and we got the 3 oxygens that it's bound to. Hopefully you remember that nitrate is NO3 minus. Okay, and then I'm going to give everybody their octet right here. And you'll notice that 5 plus 3 times 6 plus 1, that's going to end up being 24 valence electrons. And you'll notice that this lone pair gives you 2 extra lone pairs in the count. So we actually have to erase a couple of these and then make a double bond out of it. Now that gives nitrogen its octet, but it does put a formal charge on nitrogen, right? Nitrogen wants 5, it has 1, 2, 3, 4. So it's going to be a positive 1 charge on the nitrogen. So then we have to look at the rest of the formal charges on these elements. So we've got oxygen is 0 here because it wants 6. It's got 2, 4, 5, 6. So we're good on that oxygen there. This one wants 6, but it's got 2, 4, 6, 7. So that's going to be a -1 charge. So I'm going to put minus, and then this one's obviously a minus as well. And then we'll bracket this guy. Let me go ahead and erase this 6 over here, and then I'm going to erase this here so we can get the. Okay, and this is going to have an overall minus charge. Now, if we look at the bond order, remember, bond order is equal to bonds over, think of it as the bonds over atoms, right? So we got 1, 2, 3, 4 bonds. It's going to be 4 bonds over 1, 2, 3 atoms, okay? 3 atoms that are bound to the center atom. So it's going to be 1.33 bond order, which is obviously lower than 1.5. So in terms of the weakest and the shortest, weakest and the longest, we're going to expect the NO from NO3 minus to be the longest. And then I'll put /weakest. And then here I'm going to put NO plus as the shortest /strongest. Okay. So in theory, when they're asking us which one's the most difficult to break, obviously the one from NO plus, because it's a lot stronger of a bond. It's got a bond order of 3, and it's shorter, so it's a lot more difficult to break. All right, that will finish it for problem set 12. I hope you have a bit more comfort, like if you're a little bit more comfortable drawing Lewis structures. Remember to follow these rules. Hopefully you were able to get these down, even just as we were practicing them. To remember, have the center atom, draw a skeleton, make sure we match that we get everybody in octet, match the valence count, and then assign formal charges. And then if you need to, after that, put the most electronegative charge or most negative charge on the most electronegative atom. All right, we'll see you in the next problem set.